And the sum, and you might wonder, is this useful? And the answer is, it is very useful in physics, because we need to evaluate these sums in order to understand the Casimir force. Now, if you don't know what the Casimir force is, this is Professor Casimir, and he had a remarkable idea. He discovered the Casimir force, and this is his idea. If you have two parallel plates, metal plates, and there is no electric charge on these plates, no electric charge, just two infinite parallel metal plates, okay, they will feel an attraction due to quantum mechanics. And why is this? The reason is that outside the plates, there are standing waves, and these waves extend to infinity. And over here, there are standing waves. And in between the plates, there are also vacuum fluctuations, which are represented by standing waves here. And now, what happens if we move the plates a little bit? If we separate the plates a tiny bit, these waves that extend to infinity will not change. And these waves that extend all the way to infinity will not change. But the waves in between the plates will change. And if you sum up the infinite number of energies in these waves, the 0-point energies, okay, now that sum looks like a divergent series, but you can use complex variables to sum those series. And in fact, you need to sum both of these series. You need to sum this series, and you need to sum this series to calculate the Casimir force. But if you sum the series, you will find that these plates are attracted to one another, even though there is no electrical charge on the plates. Okay, that is called the Casimir force. And in fact, there's a very nice movie that I recommend you see if you have not seen it. And the movie is Indiana Jones and the Last Crusade. Okay, because in this movie, this is just an adventure movie, but in this movie, you will see a beautiful, dramatic example of the Casimir force. Okay, and in this movie, what you see is the good guy. This is Indiana Jones over here, and he is in a speedboat, and the speedboat is driven by his girlfriend. Okay, and the bad guys are after Indiana Jones. They're in a boat behind Indiana Jones. Okay, so he has his gun, but they have machine guns, and they're about to kill him. And what happens is the boat is going along, and they see two big boats in the water. Now, Indiana Jones knows about the Casimir force, and he knows that this boat is attracted to this boat, and those two boats will come together. Okay? And he yells at his girlfriend, "Don't go between the boats." And his girlfriend can't hear him because the engine of the boat, the motor of the boat, is too noisy. And she says to him, "Are you crazy? Because of the Casimir force, you should never go between the boats." Okay? And he says, "Don't go between the boats." And she thinks he said, "Go between the boats," because she can't hear him very well. And they do just get between the boats, but the boat that is chasing them blows up. And that's the end. That's how he escapes from his enemies. And it's all because of the Casimir force. And you know that if you speak with a sailor, someone who knows about boats, you never park two boats parallel to one another, because the boats will come together because of the Casimir force. Okay, so finally, complex variables helps us to understand real functions. And as an example, take the square root function. The square root function is very confusing because, as you know, there are two answers. Why are there two answers? Okay, so of course, here's one answer and here's another answer. But why is it that a function can have two possible values? You would think that's impossible. A function can only have one answer. Why is this? And the reason is that the square root function is defined on a Riemann surface. So a Riemann surface is two complex planes together, glued together, and it looks like this. Okay, so there's one complex plane and another complex plane. And what you can see is that this is called the branch point. If you're on this complex plane, okay, and you go around the branch point, you are on the other complex plane. And if you continue rotating, you go down to the first complex plane. Okay, so why are there two answers? It's because there are two complex planes, and if you go around twice, you come back to where you were. Okay? So the square root of 1 is either +1 or -1, and that's because there are two sheets in the complex plane. So like a Mobius strip, if you go around twice, you return back to the starting point. Okay, and there are lots of things that remain the same when you go around twice. For example, a Mobius strip, except this is a Mobius strip stake. Okay, if you go around twice, you come back to the same point. But in physics, there's something very important, and that's an electron. If you walk around an electron 360 degrees, it does not look like the same electron. But if you go around a second time, it does look like the same electron. And I would like to give you a demonstration of that. Here's my cup of coffee, and I must be very careful not to spill the coffee. So what I'm going to do is I'm going to rotate to this cup of coffee around 360 degrees. Now watch me very carefully. I'm going around, 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 and around. And I've now gone 360 degrees, but it doesn't look the same because my arm is twisted and it hurts. So I'm going to go around another 360 degrees without spilling my coffee. I'm going to bring it around behind my head, back to where I start. And now you can see this is how I began. So if I went around once, that was not good. I had to go around twice. And I think this means that I'm an electron. Okay. So what I've done is I've tried to explain to you that complex variable theory is very important. And in fact, complex numbers are used all the time in modern physics. Okay? But I want you to remember that complex numbers were not used until quantum mechanics was discovered. So in the theory of electricity, in the theory of fluid dynamics, sonics, all that does not use complex numbers. Even relativity does not use complex numbers. But modern physics, quantum mechanics, does use complex numbers. And you can see this is the Heisenberg algebra, and here is the number I. Okay, and this is a complex number that is fundamentally in the theory. And here is the Schrodinger equation. Don't look at the girl, okay, just look at the equation, okay? And you can see in this equation, there's an I in that Schrodinger equation, okay? And Wigner explained to us that time reversal, T, time reversal, corresponds to complex conjugation. That is, time reversal means changing the sign of I. And you can see that in the Schrodinger equation. If you change the sign of I, that is exactly the same as changing the sign of T. Okay, now, when you learn quantum mechanics in school, you learn that in quantum mechanics, a particle in a potential well, so we're putting this particle in this potential well, and this particle has quantized energy levels, quantized energy levels. And you learned that going from one energy level to another energy level is a discrete quantum leap. It's a jump. You go from one energy level up to another energy level, okay? But complex variable theory, complex analysis, explains that much, much, much better, okay? And I'm going to show you a much more beautiful understanding of what is really happening when you talk about different energy levels. And as a very simple example, I want you to imagine a two-state quantum system having energies A and B. So it's described by this Hamiltonian. There's one energy A and another energy B, and these states are not interacting, okay? Now, this guy over here is not smart enough to understand what I'm saying. He's not smart at all. He's a pretty stupid guy, but you understand what I'm saying, okay? So now what I'm going to do is I'm going to couple the states. So with a coupling constant G, I'm going to couple the state A with the state B, and this is my interacting Hamiltonian, okay? Now, if you want to know what are the energy levels of this Hamiltonian, you need to take the determinant of the Hamiltonian minus E, okay? Minus the unit matrix times E, the identity matrix times E. And if you take the determinant, you get this equation, and you set this equal to 0, and you find the roots, and you find that the energy, there are two energies, and this is the formula for the energies, okay? And you notice, you remember what I said before, I said that complex variable theory is very important in explaining the square root function. And you notice that this energy has a square root function in it. And the singularities, the square root singularities, occur where the argument of this square root vanishes. That is, in the complex G-plane, there are square root singularities in the complex G-plane where this is 0. So that's where G is equal to the absolute value of A minus B times I divided by 2. These singularities are called Bender-Wu singularities. Well, that function is a smooth function defined on a two-sheeted Riemann surface. And this is what the Riemann surface looks like. These are those two singularities. And what you see is that on this complex coupling constant Riemann surface, the energy levels are not discrete. You don't have to make a quantum leap. If you're on sheet 1, which is one eigenvalue, and you want to go to the second eigenvalue, you can go smoothly, very smoothly around here to the second eigenvalue. So for this value of G, there are two answers. And that's because when you have a square root function, there are two answers. So if you start at this energy level and you go around, you come to this energy level. And if you go around again, you come back to the first energy level, and you notice that there is not quantum leap. It is a very smooth transition from one energy to the other energy. So on this complex coupling constant surface, the energy levels are not discrete. In fact, what you see is that quantization is topology. It's topological. What you see is that the quantized energy levels correspond to the discrete sheets in a Riemann surface. each sheet, this sheet or this sheet, the top sheet or the bottom sheet, corresponds to an energy level, okay? And furthermore, the square root singularities here, these square root singularities, explain why it is that if you calculate a perturbation expansion, why does that perturbation expansion diverge? It's because there are singularities in the complex coupling constant plane, okay? And these are the singularities, okay? So if you were to expand this function into a series in powers of G, it would have a finite radius of convergence. Why? Because there are singularities here and here. The origin is over here, okay? And furthermore, as I mentioned to you before, although I didn't explain it, complex variable techniques can be used to sum a divergent series. Okay, so in other words, he's not smart enough to do this, but you're smart enough. All you have to do is imagine a parking garage. You know, you drive into the parking garage and you drive around and around and around, and you go to a higher and higher level, and you notice it's smooth. There is no abrupt quantum leap from level to level. You can go smoothly from level to level to level in a parking garage, and that is what happens in quantum mechanics. Quantum mechanics looks like it's quantized in discrete energy levels, but only if you look on the real axis. So this is the real axis. If you cut this parking garage along this real axis, you say, oh, look at all these discrete energy levels. But they are not discrete. If you look in the complex plane, they're nice and smooth, and you can go around and around smoothly from one energy level to another. So unlike what is taught in conventional quantum theory courses, energy levels smoothly deform into one another under analytic continuation. You don't have a quantum leap. The energy is smooth, just like a classical system. And in fact, a quantum mechanical system behaves a lot like a classical system in the complex plane. Okay, now this sounds like mathematics, but it isn't. It's not mathematics. What I am talking to you about is physics. And in this paper, in Physical Review Letters, they were able to take a quantum system that is a microwave billiard, which has many, many energy levels, and they were able to smoothly continue from one energy level to the next. And an even better paper was published in 2016, and another paper in 2016, where this was done. These are papers published in Nature, okay, beautiful, beautiful papers, where they were able to do this analytic continuation in a laboratory, okay? And I want you to notice something very interesting. You notice this term PT symmetry here, okay? And that's what I'm talking to you about. I'm talking to you about quantum mechanics in the complex plane, and I'm talking to you about PT symmetry. And that is the subject of my lectures today. Okay, so the question is, what is PT symmetric quantum mechanics? And I will say it very, very briefly. PT symmetric quantum mechanics consists of extending quantum mechanics from the real axis into the complex domain. And what I'm going to show you is that if you respect PT symmetry, the eigenvalues can remain real and unitarity can be preserved even if the Hamiltonian is not Hermitian. Okay, so what I want you to remember is that a PT reflection is a simultaneous reflection of space and time, okay? And this picture comes from a book. I'll show you the book. So here's the book. And if you look at the cover of the book, you can see that picture. This is a book on PT symmetry. And if you're interested, that book will give you a nice, easy to read introduction to the theory of PT symmetry. Okay, so let me give you an early example of a PT symmetric Hamiltonian. This is it. Okay. This Hamiltonian is obviously not Hermitian, but it is PT symmetric. Why is that? Because if you do a space reflection, x turns into minus x, and p turns into minus p. But under time reversal, x does not change sign, but p changes sign. And remember what Wigner said, I changes sign. So under PT symmetry, if you change the sign of I and you change the sign of x, the Hamiltonian remains invariant. So this Hamiltonian is not Hermitian, but it is PT symmetric. Now I have to tell you, when I first saw this Hamiltonian, someone showed me this Hamiltonian, and what I said, because I had a traditional education in physics, I said, this is stupid. I said, the way I see it, this theory is crazy. And I said that because this Hamiltonian is not Hermitian. And in my courses on quantum mechanics, I was taught that a Hamiltonian has to be Hermitian. Okay. However, a little while later, I noticed that in fact, this Hamiltonian has a symmetry, and the symmetry is that H remains invariant under I goes to minus I and X goes to minus X. Okay. And then I noticed that there's a very interesting way to explain PT symmetry from the point of view of relativity. Okay. So you remember that Newton discovered gravity. And you also remember that Einstein rediscovered it. He found an even better theory of gravity. So this is Newton sitting under a tree waiting for an apple to fall on his head. And this is Einstein staring at a blackboard because he has just proved that time is actually money. And you know that's a very famous theorem of Einstein. Okay, so what does Einstein say? Einstein tells us that the Lorentz group is fundamental. And this is where complex variables comes in. So in your elementary physics course, you learned that the homogeneous Lorentz group is a 6-parameter group of real 4x4 matrices. Okay, and what do these matrices do? They transform the space-time point x, y, z, and t into x prime, y prime, z prime, and t prime. But they transform it in such a way that x squared plus y squared plus z squared minus t squared is preserved. This is a constant. Okay, so this is the light cone condition. Okay, and you know that there are some obvious elements of the Lorentz group. One of them is P, and one of them is T. Okay, now what does P do? P changes the sign of X, Y, Z, and T, but not T. Okay, and time reversal leaves X, Y, and Z alone, but it changes the sign of T. Okay, so PT changes the sign of X and Y and Z and T. So it looks very nice from the point of view of the Lorentz group. Okay, now already we can see in the Lorentz group that there are complex numbers. In fact, Wigner explained to us that if you want to describe fermions, for example, if you have a 2-component spinor, that you have to use complex representations. But Einstein didn't know about that. He was just interested in coordinate representations, X, Y, Z, and T, a point in four-dimensional space. Okay? Now, if you look at a map of the Lorentz group, this is the Lorentz group, and the Lorentz group is a continuous group, but it falls apart into four parts. Okay? This is the proper orthochronous Lorentz group, and this is a subgroup of the Lorentz group. And it contains the identity. Okay? This is another part of the homogeneous Lorentz group. Okay? These elements of the Lorentz group are all of these elements multiplied by P. And this is called, another part of the Lorentz group. It is all of these elements multiplied by T. And the fourth part of the Lorentz group are all of these elements multiplied by PT. Now, for many, many years, people thought that the natural world was invariant under all of the Lorentz group, all of these elements of the Lorentz group. However, as you know, Li and Yang, back in 1956, wrote a paper saying that it's not true, that in fact, these elements are not symmetries of nature, okay? And they won the Nobel Prize for it. And in fact, Madame Wu showed that they were correct in the laboratory. And you also know that Cronin and Fitch showed that these elements here are not symmetries of nature. They showed that time reversal is not, that the world is not invariant under time reversal, okay? So Li and Yang showed the world is not invariant under parity, P, and Cronin and Fitch won the Nobel Prize for showing that the world is not invariant under T. Well, this is the fourth part of the Lorentz group. Okay, and these are all the elements of this group multiplied by PT. Okay, so the question is this a symmetry of nature or not? Okay, now, if you extend the Lorentz group to the complex Lorentz group, then you see that there is a continuous path through group space from here to here. And so these two parts of the Lorentz group are linked in a natural way, in a beautiful natural way, if you look in the complex plane. Okay, also, this part of the Lorentz group is connected to this part of the Lorentz group in the complex plane. Okay, now, why is this important? Because if you are interested in reading a very difficult book, very highly mathematical book, very difficult, the name of the book is PCT, Spin and Statistics and all that. This is a book written by Streeter and Whiteman. And what they prove is a beautiful and powerful theorem in theoretical physics called the PCT theorem. And what they show is that if you live in the world, but you take another world that is reflected in space, that is reflected in time, and that is made out of antiparticles, C changes a particle into its antiparticle, those two worlds are indistinguishable. Experiments performed in this world and in this world are identical. They give identical results, okay? And this is a consequence of complex variable theory because you have to extend the real Lorentz group to the complex Lorentz group. So this is a very, very powerful theorem and it's very suggestive. But today we're not going to talk about particle physics. I'm only going to talk to you about elementary quantum mechanics. Okay, so the question is, how do you construct a PT symmetric Hamiltonian. And I'm going to give you a very, very simple recipe. You begin with a Hamiltonian that is both Hermitian and PT symmetric. Okay, so you begin with a Hermitian Hamiltonian that is also PT symmetric, and then you perform a PT symmetric deformation. And I'm going to explain to you what I mean. Okay. But what I mean by a deformation is, for example, that you can add or multiply by a non-Hermitian but PT symmetric quantity like I times X. So this quantity is PT symmetric. So when you continuously deform a Hermitian Hamiltonian by using a PT symmetric deformation, that Hamiltonian is no longer Hermitian, okay? But it is still PT symmetric, and this is because, remember, P replaces X by minus X, and T replaces I by minus I. And if you want to see some examples, this is a complex deformed squirrel, and this is a complex deformed frog, and here's a complex deformed bird, a parrot. Okay, so what is an example? Can I give you a very simple example? So let's take the harmonic oscillator. You all know what the harmonic oscillator is, and the harmonic oscillator is PT symmetric. It's Hermitian, of course, you know that. It is also PT symmetric because if you change the sign of P and X, because they're squared, this is invariant. So it is both T symmetric and P symmetric. Okay. Now, notice that the eigenvalues of the harmonic oscillator are all real and positive. And these are the eigenvalues. Now, I'm going to deform this Hamiltonian by adding to the Hermitian harmonic oscillator something that is not Hermitian. And this is not Hermitian. You know, the term IX is not Hermitian. I'm going to put in a real deformation parameter that I'm going to call epsilon, okay? But what you will see is that the eigenvalues of this non-Hermitian Hamiltonian are still real and positive, okay? In fact, the eigenvalues of this Hamiltonian are given by this formula, and you notice that the eigenvalues are still real and positive. So we begin with one unique Hermitian Hamiltonian, and now we have an infinite number of non-Hermitian Hamiltonians, but they all have real positive eigenvalues. Okay, and if you want to prove this, it's easy. All you have to do is write down the Schrödinger equation for this Hamiltonian and replace X by X minus I times epsilon, and you're done. Okay, and you can calculate these eigenvalues by yourself. It'll take you only 2 minutes to do it. Okay, so the eigenfunctions, of course, are complex, as in general, as eigenfunctions in general are complex, but they are still orthogonal. Okay, so we can take the position that PT symmetric Hamiltonians are fundamental, and a Hermitian Hamiltonian is just one special case of PT symmetric Hamiltonians. Okay, so
quick question.
Yeah.
When you compute orthogonalities, do you still use the Euclidean matrix in the space?
Yes, we're going to talk about that, and in fact, I will spend the last lecture today talking about what you mean by the inner product and how you define what is the equivalent of the, what is the adjoint of a PT symmetric Hamiltonian. And I will talk to you about that in general.
Thank you.
Okay. And we will derive I will explain how you define the PT adjoint, okay, to show that the theory is self-adjoint. Okay, we will talk about that. Okay, and that's going to be in the third lecture today. Okay, so just a comment before I stop, I'm going to stop in just another minute. So remember that we want the eigenvalues of a Hamiltonian to be real. Why is that? Because when you measure an energy in the laboratory, the result is real. Okay? Now, hermiticity is a very fancy mathematical condition. You know, in physics, when I define the axioms of quantum mechanics, all of the axioms are very physical. You know, I say positive probability. I say the spectrum has to be bounded below. Okay, I say that the ground state energy has to be stable. So stability, locality, these are all physical concepts. But one axiom of quantum mechanics is very, very mathematical, and it's not physical. And that's this condition, hermiticity. Hermiticity says if you take the complex conjugate and the transpose of your Hamiltonian matrix, you should get back the Hamiltonian matrix. That's mathematics. That doesn't sound like physics, okay? But hermiticity is a very powerful mathematical condition, and it does guarantee that the eigenvalues are real and also that the theory is unitary. But what I'm arguing today is that hermiticity is nice, but I don't like it because it's mathematics, not physics. And what I'm arguing today is that it is not a necessary condition. So what I'm going to show you in these talks is that there are infinitely many more PT symmetric Hamiltonians with real eigenvalues than Hermitian Hamiltonians. There are infinitely many more PT symmetric Hamiltonians. So the Hermitian Hamiltonian that I just showed you is just one special case, and it's not very different from all the other Hamiltonians. And what I was saying to you before was you might adopt the view that PT symmetry is a fundamental physical property. It's a physical condition, and it's a physical property of a quantum Hamiltonian. And hermiticity is just a simple special case. Okay? So when I begin my next lecture, I'm going to talk to you about how you prove that the eigenvalues of a Hermitian Hamiltonian are real. And we're going to look at some very fancy examples of PT symmetric Hamiltonians. Okay? So I think we should stop now and take a short break. Okay? And then in 15 minutes, I will begin again.
Okay, so can we just ask questions if anyone here has questions?
Yeah.
Okay. So PT symmetry is it somehow related to the supersymmetric quantum mechanics?
Is it you're asking if PT symmetry is related to supersymmetry? Is that what you're asking?
Quantum mechanics.
In quantum mechanics?
Yeah.
Yeah. So the answer is no. PT symmetry is not the same as supersymmetry. However, it is interesting that you can take a supersymmetric Hamiltonian and make it PT symmetric without destroying the supersymmetry. So there are a number of papers written on that, and you can look them up. I can mention them to you. So you might think that if you begin with a supersymmetric Hamiltonian and you then make it PT symmetric, you might think that this would destroy the PT symmetry. I'm sorry, that it might destroy the supersymmetry. Okay, you might that PT symmetry might interfere with supersymmetry, but it doesn't In fact, PT symmetry is compatible with supersymmetry. They don't interfere with each other at all. You can have a supersymmetric, PT symmetric Hamiltonian, no problem.
So the question is this PT condition, is it necessary and sufficient to have real eigenvalues?
You are asking, I think you asked, I couldn't quite hear you well, but I think you were asking, if you have PT symmetry, will the eigenvalues be real?
Yes. So is it
so
necessary and sufficient condition?
Right. So you're asking me, does PT symmetry imply that the eigenvalues are real?
Yes.
Is that correct?
Yes.
And the answer is no. So if you have a Hamiltonian that is Hermitian, you know that its eigenvalues will be real. If you have a Hamiltonian that is PT symmetric, the eigenvalues may be real, but they may not be real. Okay, so this is what I'm going to talk about at the beginning of the next lecture, and I'm going to show you that that if you have a PT symmetric Hamiltonian, the eigenvalues are either real or they come in complex conjugate pairs. So they can be complex, okay? If the eigenvalues are all real, we say that we have an unbroken PT symmetry. And if the eigenvalues of a PT symmetric Hamiltonian are complex, then we say we have a broken PT symmetry. And there is a transition between a broken PT symmetry and an unbroken PT symmetry, okay? And usually at the transition point, that is where the Hamiltonian is Hermitian, okay? So Hermitian Hamiltonians are at the transition between broken PT symmetry, where the eigenvalues are complex, and unbroken PT symmetry, where the eigenvalues are real. And I'm going to talk to you about that in just a few minutes in the very next lecture.
Thank you. Okay, so I think let's take a break. So we'll come back at 10:05. Yeah.
Okay. Are you able to understand what I'm saying? Am I speaking clearly enough?
Very clear, I think. Yeah, very clear.
Okay, so you're okay with the speed that I'm going at?
Yes.
Okay, good.
Yes.
Okay, so I will be back in just a moment.
Okay.
Okay.
Yes, I'm the secretary of the thank you. 老师要给我钱吗？有发现吗？
有啊。
Symmetry, okay, such as the harmonic oscillator. Okay, so what is, I think, more interesting is that if you have a non-Hermitian theory, but the theory is still PT symmetric. Okay.
Okay, thank you. So I think let's move on to the second
Okay? Now, of course, the eigenvalues have not really disappeared. What has happened is that these two eigenvalues have gone off into the complex plane. Okay? But for positive epsilon, the eigenvalues are all real. For negative epsilon, the eigenvalues can be just doing classical mechanics, and we ask how long does it take for the particle to reach infinity? And what you see is that it takes a finite amount of time to reach infinity. Okay, there's no question about that. It reaches infinity in finite time, and you know how to write down Newton's equation and solve it. Okay, this is first year undergraduate physics, very elementary problem, and this is the exact amount of time it takes for the ball to reach infinity if it begins with an energy E. Okay, and the question is, where does it go next? Where is that ball when the time is t plus 1? Where is that ball? Okay, so to explain to you what is going on, I'm going to first talk about the harmonic oscillator. I'm going to talk about what happens if you extend the harmonic oscillator into the complex plane. What I'm going to show you is that you don't know the answer to that problem unless you understand complex variables. Without complex variables, you cannot solve that problem. It's a very simple problem, okay? And we're going to begin by studying classical harmonic motion. So the very first topic, when you go to college and you're a first year undergraduate student, what do you study? In physics, you study the harmonic oscillator. And this is what you learn. You learn that if you have a particle on a spring, here's the particle goes back and forth. It goes all the way out to a turning point where the spring is stretched maximally. Then it stops and it turns around and it goes back again, and it goes to the other maximum point and it goes back and forth. So you have oscillating motion, okay? And what you learn about is classically allowed regions and classically forbidden region. So here's the particle on the real axis, and it's going back and forth, and this is the classically allowed region. The particle cannot go here because if the particle were to the right of this turning point, okay, where is this turning point? The turning point is where p equals 0. So the turning point is where x is equal to the square root of e. Now, if x is bigger than the square root of e, then x squared is bigger than e. But if x squared is bigger than e, then p squared is negative, and p squared cannot be negative. So this is called the classically forbidden region, and this is the classically forbidden region here. And you all know that, and this is trivial, right? But, and in fact, if you need to explain this to somebody, this is the classically allowed region, and you can't see the classically forbidden region over here, okay? But we can ask, what about the classical harmonic oscillator in the complex plane? Okay, so we only talk, this is the complex plane now, and we were talking about the particle going back and forth between the turning points. If you have a particle in the classically forbidden region, remember I said this is where p squared is negative. But if p squared is negative, it says that p is pure imaginary. So the velocity of the particle is actually in the imaginary direction. So if you want to study the harmonic oscillator in the complex plane, the particle is allowed to be in the classically forbidden region, but it is going in the imaginary direction. Okay, let me go back. It's going in the imaginary direction. Okay, so where does it go? So it goes like this, and then it comes around like this, and it goes back to where it started. So the particle is in an orbit, and for the harmonic oscillator, this orbit is an ellipse. And in fact, the turning points are the foci of the ellipse. So the possible classical motions of the complex harmonic oscillator are not just back and forth on the real axis, but they go around and around in the complex plane, in an ellipse. That's what the classical motion is, okay? Now, if we put in this is with epsilon equals 0. Remember the epsilon? There's an ix to the epsilon. Remember that. So if we set epsilon equals 1, we get p squared plus ix cubed. And here are the turning points. And the turning points have moved downward into the complex plane. And instead of the particle orbits being ellipses, these are transcendental functions. Okay, they're elliptical functions. But the particle goes in a closed orbit. So the particle goes back and forth between the turning points in the complex plane. But if it doesn't begin on a turning point, it goes around in an orbit. Okay, in fact, what we learn from this picture is that the particle is not really going back and forth. If you think about the harmonic oscillator in the complex plane, this motion back and forth is not really back and forth. It's a degenerate ellipse. The particle is going infinitesimally above the real axis. It goes around the turning point. It's turning. It's going around the turning point and going back infinitesimally below the real axis and going around the turning point and going like this. It's in a degenerate ellipse. Okay? Now, if you have a p squared minus x to the 4 theory, there are 4 turning points. And if you study this in the complex plane, the particle is going back and forth between the turning points. And then there are an infinite number of closed orbits that go around the turning points. These are not ellipses, they're deformed ellipses. Okay, and now we ask, what happens if you roll a particle down a hill and the hill is a minus x to the 4 hill? What happens to that particle? Okay, well, that means that although we understand what is going on in the complex plane, we must approach the real axis over here. What happens as we approach the real axis? Well, as you get closer and closer and closer to the real axis, the particle is traveling very close to the real axis, and then it goes all the way out around like this and comes back up to the origin. So as we approach the real axis, what happens? Well, the particle goes all the way off to infinity, and then it makes an enormous loop traveling infinitely fast. And it comes all the way back up the negative axis, right back to the origin again. That's what happens, okay? Now, it turns out that by Cauchy's theorem, remember, the time that it takes to go in an orbit is an integral. And Cauchy's theorem applies to integrals, and the time integral is the same for all orbits because of Cauchy's theorem in the complex plane. So the amount of time to go back and forth like this is the same as the amount of time to go around like this, or like this, or like this. So what happens is the particle travels down the real axis in finite time. It then travels infinitely fast around to minus infinity over here and travels back to the origin. But the particle is traveling slowly near the origin and very fast when it's far from the origin. So the particle spends almost all of its time very, very close to the origin. So it is in a dynamical bound state. It's not in a static bound state, it's in a dynamical bound state. Okay? So if you ask, what is the probability of finding this particle? It is most probable to find the classical particle near the origin, and it's very unlikely to find the particle very far from the origin because it's traveling very, very fast. So in fact, the particle spends almost all of its time very, very close to the origin. This is a sharply peaked probability distribution. So the particle is in a static, is not in a static bound state, it's in a dynamical bound state. Okay, so remember, PT symmetry refers to dynamical stability, not static stability. So the particle is not balanced on top of the hill, but rather it spends all of its time, almost all of its time, very, very close to the origin. Okay, so again, what is the particle doing? It's going very, very slowly here. This is where the particle is most probable to be found, and then it goes whizzing around, comes back up the negative axis, back to the origin. Okay, so a system with static instability becomes dynamically stable in the complex domain. And this is something that nobody ever noticed before, that if you go into the complex plane, you can have dynamic stability, not static stability, but dynamic stability. And that's the reason why we can have stable quantum bound states, okay? So the instability, the static instability at x equals 0 is tamed. Complex mathematics helps you to tame instabilities. And what you see is that physical systems that seem to be unstable can become stable in the complex domain. Okay, so there are lots of examples of dynamically stable systems. For example, when you ride a bicycle or when you have a top, okay, spinning top, that spinning top is dynamically stable. It's not statically stable. If you stop, if you are not rolling forward on your bicycle, if you just stop, you fall down. But if you're moving, you stand up. So you're stable when you're moving. And that is what is happening here in the complex plane. Okay, so why is this true? Well, when you extend the real numbers to the complex numbers, nothing changes except for one single thing. When you go to the complex numbers, you can't say greater than or less than. If you have two complex numbers, you can, A and B, you can't say A is bigger than B or A is smaller than B. Can't say that. Okay? So when you say a physical system is unstable, what you mean is that it doesn't have a ground state. It can fall down. Okay? But when you say the system is unbound, the energy is unbounded below, you are using a symbol like this. And when you're talking about complex numbers, you cannot use that symbol. So physical systems that look unstable may not be unstable, like bicycles and tops. Okay? Now, I'm going to give you a proof that the quantum, that this Hamiltonian has real positive eigenvalues. Okay? So this is a very simple proof. It's freshman calculus, nothing more complicated than calculus. And this is the only case, the only non-trivial case I know where I can actually prove it to you in 2 pages. Okay, so are you ready? I'm going to show you a proof that, not just a classical proof, I'm going to talk about the quantum system. I'm going to show you that this quantum Hamiltonian has eigenvalues that are real and positive. Okay, even though this is an upside down potential. Okay, so this is the Schrodinger equation. And you remember that we require that the boundary conditions are that the eigenfunctions vanish in this direction, and they have to vanish in this direction in the complex plane. And what I'm going to do is take a particular curve and I'm going to parametrize this curve in the complex plane. So I'm going to say, let x be given by this expression, that this is this curve, where y is a real number. Okay, so y goes from minus infinity to infinity, and as y goes from minus infinity to infinity, x comes up here and goes down here. So instead of writing the Schrodinger equation in terms of x, I'm going to write it in terms of y, and it's a mess. It's kind of complicated, okay? But don't worry about that, because that's just algebra, okay? Now I'm going to take this equation, and I'm going to take the Fourier transform, okay? If I take the Fourier transform of this equation, I get this equation. And I simplify this equation, and this is what I get. Okay, and next, what I'm going to do is you notice this equation here has a 2 derivative term, and a 1 derivative term, and a no derivative term. Okay, and I'm going to do a simple transformation to get rid of this 1 derivative term. And the transformation is just this. I'm going to replace the dependent variable by this expression times another function, where this expression dependent Schrodinger equation for, notice, a positive quartic potential. So do you understand what I'm saying? We began with a negative quartic potential, and just by changing variables, I end up with a Schrodinger equation that has a positive quartic potential and also a linear potential. Now, the linear potential is negative, but I don't care about that, because a quartic potential is much bigger than a linear potential. So the potential is a rising potential, and it has a positive spectrum. And that's the proof. Okay? So in other words, the Hamiltonian for this new Schrodinger equation is this, and you notice this Hamiltonian is p squared plus z to the 4, and then a linear term. So this is a rising potential. You notice what we did. We began with this potential, which is an upside down quartic potential, and we ended up with this potential, which is a positive quartic potential. And you know that the eigenvalues for a positive quartic potential are positive eigenvalues. Why are the eigenvalues positive? Because these are stable states, and they are stable states at the classical level and stable states at the quantum level. And this is really beautiful. I mean, this is one of the most beautiful things I've ever seen in my life. Okay, because I'm showing you something that's absolutely amazing. If you roll off to infinity, you are not gone. You actually spend all of your time at the origin, okay, in a bound state. You do not escape to infinity. You do not stay at infinity. So if you ask, where is the particle at t plus 1, it's back near the origin. That's where it is. Okay? So the only thing is, let me show you this again. You notice that this term is proportional to h bar. And if you know something about quantum field theory, people talk about anomalies. You notice that this new Hamiltonian contains h bar explicitly. Okay? It contains h bar explicitly. And therefore, this is called an anomaly. And what this is a parity anomaly. This is the remnant of the PT symmetry. The parity symmetry, because we did a Fourier transform, the parity symmetry is not at infinity, but rather it's at the origin. And this Z vanishes at the origin. So we have, by doing a Fourier transform, we've taken some very strange behavior at infinity and moved it down to the origin, but it's proportional to h bar. And this is called a parity anomaly. Okay, so this upside down potential has exactly the same eigenvalues, exactly, as this potential, and this potential is a conventional right side up potential. This is Hermitian. Okay, this is Hermitian. It has real energy levels, and these real energy levels equal these because it is the same E. E has never changed. So in the calculation I showed you, I began with an E for the upside down potential, and when I finished the calculation, there's E for the right side up potential. E for one potential is the same as E for the other potential. So it's amazing that what you think is bound states, these are not, so you think of these as unstable states, but they're not unstable, they are bound states, even though we have an upside down potential, and that's amazing, okay? And if you look at the classical motion, if we take the original potential and ask, how does this particle travel in the complex plane, it goes around like this, okay? And if you ask, how does a particle travel in this potential, it goes around like this, okay? But it's very interesting, although they have the same quantum energies exactly, all of the quantum energies of one potential are equal to all of the quantized energies of the other potential. At the classical level, notice we have an H bar, but in classical mechanics, H bar is 0. So therefore, at the classical level, where I set H bar equal to 0, these two orbits are not the same. The period of the orbits is not the same. And if you set H bar equal to 0, it takes a different amount of time for the orbit to close. So the orbit wants to close, but it didn't have enough time to close. Okay, so these two systems are exactly the same at the quantum level, but they differ at the classical level, which is very, very, very interesting. So let me explain intuitively how you can understand this. So imagine you have a potential that looks like a staircase. Okay, you understand quantum mechanics, and you know that if I have a particle at the top of this staircase, what will happen to a wave function? This is a rabbit. What happens if I write down the wave function for a rabbit? Well, the wave function spreads, right? And when it reaches this point, it reflects, it diffracts, okay? And part of the wave function goes back and part of it goes forward. Then the wave function continues to spread and part of it goes backward and part of it goes forward. And if you arrange the staircase right, a little bit diffracts back, more diffracts back, more. And in fact, the wave function never reaches infinity. So although the classical rabbit is hopping all the way down to infinity, a quantum rabbit never gets to infinity because it keeps getting diffracted at each point. And what I have been talking about is the continuum version of this staircase. Okay, so this is an intuitive way to understand the nature of stability. Okay, so this is what I've told you. I'm going to summarize what I've told you so far. If we have a right side up potential, you have a bound state in this potential. If I make it an upside down potential, like this, then you learn in your conventional quantum mechanics course that this particle now is unstable and it tunnels out to infinity, right? That's what you learn in your quantum mechanics course. And this is not an equilibrium situation, okay? Because the particle in this potential well is gradually disappearing and the particle is traveling out to infinity. But what we are talking about is particles, is a system with gain and loss. So the particle travels out to infinity and comes back up from minus infinity. Out to infinity, around, and back up from minus infinity. So this is the gain, and this is the loss, and they are in balance, and therefore the state in the middle is not going down, and it's not going up. It's in dynamic equilibrium. And that is what is happening in a PT symmetric Hamiltonian. We have dynamic equilibrium. Okay? And I hope you understand what I'm saying. This is not trivial. This is really very, very, very subtle. Okay? But we have a balanced loss and gain. And we have that balanced loss and gain at the classical level and at the quantum level. Okay? It happens classically and quantum mechanically. Okay? So this is called unidirectional scattering. We first, I wrote a paper with a guy in India and Michael Berry, who's known for the Berry phase, on reflectionless potentials, upside down potentials with PT symmetry. I wrote another paper with a colleague on this. This reflectionless scattering was observed in PT symmetric optical scattering systems. And this is just one paper where they observe this, okay? And I mentioned at the beginning of my talk that we just wrote a physical review letter on cold atom scattering off a minus x to the 4 potential or minus x to the p potential on the real axis, okay? And you can read this paper. This is just a few weeks old, where we should be able to observe those energy levels in a simple cold atom scattering experiment where you have loss and gain, balanced loss and gain. Okay? So now I have about maybe 15 minutes, and I'm going to show you so I should ask you, that is a very basic introduction to PT symmetry. And I thought that you might be interested in some more advanced problems just involving simple quantum mechanics. Shall I tell you about that?
Yes, please.
Okay, so I will go faster now, and maybe you will have a feeling for some of the interesting things you can do with studies of PT symmetry, just one-dimensional PT symmetry, okay? So, for example, instead of an x to the 4 Hamiltonian, let's take an x to the 6 Hamiltonian. Now, you know that if you set this equal to E and you calculate the turning points are here. There are 6 turning points because the turning points satisfy the equation x to the 6 equals E, right? So in the complex plane, we have 6 turning points. And if you ask, how do classical particles move? Well, there's the one example you know from your elementary physics course is that the particle can roll back and forth, because this is an x to the 6 potential well. It can just roll back and forth in the potential well and go back and forth like this. And if you ask, how does the particle move in the complex plane? It goes around like this. Okay? But there are these 2 turning points and these 2 turning points. Okay? So if you start a particle here, it goes back and forth between this pair of turning points. And if you don't go back and forth, it goes around and around, okay, around and around. And in fact, there are 3 regions of classical orbits. There's this region here, there's this region here, and there's this region here. There are 3 types of classical orbits. This is classical motion. okay? And these orbits fill the complex plane, okay? But what happens if we take the energy of the particle not to be real? We take it to be slightly complex, okay? So the energy is not real. It has a slight complex part to it. What happens now if the energy is complex? Well, the particle, this is a plot of the particle. It's a little bit hard to see this, but the particle starts over here and it goes around and around, and it comes, instead of 3 separate regions of classical orbits, the particle goes around and around. It goes into another region. It leaves that region, goes into another region, and it jumps from region to region. So it is tunneling. So in this picture here, these orbits are isolated orbits. They cannot mix. But if the energy is slightly complex, now the classical particle can tunnel from this region to this region. Okay? So we see a tunneling classical particle. Tunneling from classical region to region. And in fact, what we see is deterministic random behavior. Here is the classical particle. It is in one region, then it jumps to another region, then it jumps to this region, then it jumps back up to this region, and it jumps, and it goes back and forth in a chaotic fashion. So we have deterministic classical random behavior. Okay? And here is the same example for an x to the 10 potential. And this is very interesting because we have classical motion in this region, classical motion in this pair of regions, classical motion here, classical motion here, classical motion here. And at the quantum level, we have, this is the standard Hermitian quantum mechanics problem. This is a PT symmetric quantum mechanics problem. And here's a different PT symmetric quantum mechanics problem. You notice left-right symmetry of the turning points. And what you see is that the energy levels in the conventional problem are these numbers. These are the energy levels. In this pair of turning points, we have bigger energy levels. And in this pair of turning points, we have an even bigger energy levels. And this is very interesting because for the same Hamiltonian, p squared plus x to the 10, we have 3 different spectra. If you think about the real world, you know, there are 3 kinds of leptons. Okay, 3 kinds of leptons. They have almost identical properties, except that the masses of the leptons get bigger and bigger and bigger. So it is possible that when you talk about the electron and then the muon and then the tau particle, which is much heavier than the muon, and the muon is much heavier than the electron, what you could be seeing is the complex plane. Exactly the same Hamiltonian for the electron. When you study it in the complex plane, it has higher energy levels and a bigger mass. Okay, and if the energy is slightly complex, you can tunnel back and forth. And that's what happens in real life. Given a tau particle, it can decay into a mu particle. Okay, and the mu particle can tunnel, it can decay into an electron. Okay, so what we're seeing is the possibility of explaining the real world in terms of the complex plane. Okay, which is really interesting. Okay, and I'm going to show you some of the orbits. Okay, so here is an example of a Hamiltonian. This Hamiltonian has an x to the 4 rising potential and has a negative quadratic potential, so the potential looks like this. Okay, So what is the classical motion? So if you take the energy to be -1, so this is -1 over here, what does the particle do? It goes back and forth, okay? If you put a particle in this well, it goes back and forth. So it goes back and forth here, okay? But if you put a particle in the complex plane, it goes around and around. But notice that this particle here cannot cross to here. You cannot tunnel. A classical particle is not allowed to tunnel from this well to this well, even in the complex plane. So all of these orbits stay to the right, and all of these orbits stay to the left. And no orbit can go from this side to this side, okay? So it can't do that on the real axis, and it cannot do that in the complex plane. But if we make the energy complex, now the particle spirals around, it crosses over here to this, it goes into this well, it comes back out again. So the particle can tunnel back and forth through the complex plane. And that's very interesting, because if you study tunneling in quantum mechanics, while the particle is tunneling, where is it? And you don't know where the particle is when it's in the process of tunneling. And that's because the particle is in the complex plane. You cannot say where it is, it's simply traveling through the complex plane. Okay, and that is exactly what is happening here. So if you give the particle a little bit of complex energy, it tunnels back and forth. And what is really interesting is you can ask, how long does it stay in this well until it tunnels to this well? Okay, and it turns out that if you multiply the imaginary part of the energy times the average time spent in a well, it's a constant. And so although this is classical physics, we see a time energy uncertainty principle in classical physics, which is really interesting. So this shows you that complex mathematics is really, really interesting, okay? And furthermore, you can even see resonant tunneling. So if you're very clever, you could choose exactly this number for the imaginary part of the energy. And if you do, the particle starts here, it goes around, and it goes right into the other well. And this is resonant tunneling. It doesn't take forever to go into this well. It doesn't do random behavior. It goes directly to this well and bounces back again. And it goes back and forth from well to well as if there is no gateway. There's no problem about going back and forth. So this is resonant tunneling at the classical level. This is an even more complicated resonant tunneling. And I want you to see something really interesting. How does the particle go from this well, the right well, to the left well? Okay. Well, the blue particle starts here at this turning point. It goes around and around and around and around and around, and it ends at the turning point in the other well. Okay. But what does the red particle do? The red particle goes around and around and around, and it goes faster and faster, and it goes off to a minus I infinity. And then it comes back down from plus I infinity, and it goes around and around and around and ends over here. So I want you to notice that the red particle goes from the right well to the left well, but it never crosses x equals 0. It never crosses this line. So you can go from one side of the universe to the other without going through the middle of the universe, because what the particle is doing is going off to infinity, minus I infinity, and coming back from plus I infinity, which is really amazing, okay? Okay, so you can see how much fun you can have doing complex quantum mechanics and complex classical mechanics, okay? And this is a really fancy example of that kind of a plot, okay? Now, let me see. I'm not going to talk about this, but so this is, you have to give some sort of conclusion, and this is an overview of my talk so far, and I noticed that somebody is sleeping back here. This is me standing talking to you, and somebody has fallen asleep. So I promised to say something about the theory of the model, to talk about the inner product and so on. There are quite a few slides left. So you can ask, is this quantum mechanics? You can ask, can you find an inner product that is positive definite? Okay, the eigenfunctions must be orthonormal with respect to this inner product, and you have to show that time evolution is unitary. Okay, and I have a feeling it's getting late for you, and I probably shouldn't explain it to you, but maybe I will just say 1 or 2 words about it if you would like. I should ask you, would you like me to just summarize what this is saying?
Yes. Please.
Yes, please.
Okay, so I will try to say something in just about 2 or 3 minutes, just to give you a feeling for why what I've been talking about when I talk about complex quantum mechanics, why this is real quantum mechanics, okay? I'll try to explain that to you. And in fact, what I'm going to do is, I have slides, but there are too many slides here. And so what I'm going to do is, I'm just going to do this on a piece of paper, and I'm going to show you, I'm going to just write some equations down and show them to you. Is that okay?
Yes. Yes.
Okay, so I'm going to stop sharing my screen, and can you see me better? Can you see the picture of me better?
Yes.
Okay, so this is the theory of PT symmetric quantum mechanics, and what I'm going to explain to you is this. In PT symmetric quantum mechanics, what you know is that the Hamiltonian commutes with the PT operator. If this is true, if the Hamiltonian commutes with the PT operator, that means that you have PT symmetric quantum mechanics, okay? Now, you remember that I said to you that there is a region of broken PT symmetry and a region of unbroken PT symmetry. In the region of unbroken PT symmetry, the energies are real, okay? But there is something else that is really remarkable, and that it took me a long time to understand, okay? Many years before I understood this point. If you are in a region of unbroken PT symmetry where the energy, all of the energy levels are real, the Hamiltonian has a secret symmetry that I didn't know about for several years, okay? What that means is that there is another operator that commutes with the Hamiltonian, and I call this operator C, okay? So the C operator also commutes with the Hamiltonian, okay? So I have to say this again. If you have a Hamiltonian that is PT symmetric, which means that PT commutes with the Hamiltonian, sometimes the energies are all real, and sometimes the energies are not all real. They may be complex. Okay? Now, if you have a situation where all the energy levels are real, it means you're in a region of unbroken PT symmetry. And if you are, that Hamiltonian has another symmetry that guarantees that all the eigenvalues are real. That symmetry, to express that symmetry, there's a new operator that we don't know about. And that operator is called C. Okay? And that operator C, just like PT, C commutes with the Hamiltonian. Okay? Now, the whole key to understanding PT symmetry is to understand that C operator. Okay? So the C operator has three properties. Okay? The first property is, number one, is that C commutes with the Hamiltonian. Okay? Number one, C commutes with the Hamiltonian. Okay? Number two, C commutes with PT. So the operator C is itself PT symmetric because C commutes with PT. That's the second equation. That's equation number two. Okay? And equation number three, this is the last equation. Equation number three is that C is a reflection operator. That is, C squared equals 1. Okay? C squared equals 1. Now, these are three equations. C commutes with the Hamiltonian, C commutes with PT, and C squared is 1. Now, those are three simultaneous equations, and if you want to know what the C operator is, you have to solve those three simultaneous equations to calculate the C operator. Okay? That's not easy. It looks like it's going to be easy, but it's not easy. However, you can do it approximately, and you can calculate the C operator. Okay? So imagine you have now calculated the C operator. What do you do with it? Okay? And the answer is you construct the inner product. Okay? And how do you define the inner product? Well, you take a state. This is a state, let's call it psi. This is a state in a Hilbert space. Okay? What is the inner product? Well, you know that this is called a ket. Okay? The inner product looks like this. In conventional quantum mechanics, that's the inner product. Okay? And what is this bra over here? That is psi star. Okay? That is not psi star, but psi dagger. In other words, if you have a state, you dot it into its Hermitian conjugate, and that is the inner product. Okay? In PT symmetric quantum mechanics, you construct the CPT operator. Okay? So if you have a state in your Hilbert space, and you want to know what the inner product is, you take that state and you multiply it by CPT. Instead of dagger, you use CPT. And the inner product is what you get if you dot the CPT state into the state. And that inner product is a positive inner product, and that is the probability that you need to measure when you do an experiment. That's the probability of the outcome of your experiment. And that probability is a positive definite quantity. Okay? So that is the general, that's the complex. So now you understand, that is the complex generalization of conventional Hermitian quantum mechanics. And what you need to do is to construct the CPT inner product. And this is very much like the famous CPT theorem in particle physics. Okay, it has a very strong analogy if you know about the CPT theorem. Okay, and so the CPT inner product exhibits unitarity, that is conservation of probability, and the probability is a positive number. And so everything I have been talking to you about today is not just mathematics, it is physics, because that is the thing that distinguishes quantum mechanics from some other silly theory. Okay, in quantum mechanics, you have an experiment, and when you make a measurement, you measure a probability, and that probability must be positive. And in PT symmetric quantum mechanics, there is a probability. And the only difference is that in conventional quantum mechanics, you already know what the definition is of an inner product. It's just psi dagger psi. Okay? But in PT symmetric quantum mechanics, you don't know what the inner product is until you calculate the C operator, which is not trivial. But when you calculate the C operator, it's not psi dagger psi, it's psi CPT psi. Okay? So what I'm telling you is that the Hamiltonian determines its own inner product. You don't know the inner product until you solve for the C operator. And that takes work. You have to do that. But that's how the theory of PT symmetric quantum mechanics works. Okay? So you can read about it. I showed you this book. There's a whole chapter on the C operator and how to calculate the C operator. Okay, and you can learn about the inner product. And this is the rigorous quantum mechanical interpretation of what I've been telling you. I've been telling you a lot about differential equations and energy levels and so on, classical orbits and so on. But in fact, this is a true theory of quantum mechanics because we have the theoretical underpinning of the theory, okay? We have unitarity, we have an inner product, we have a positive inner product, and therefore, this is an exact, strict, rigorous theory of quantum mechanics. Okay, so I hope you found this interesting. Thank you very much for listening. And if you have more questions, I'm very happy to try to answer them.
Hello, Professor Bender. Thank you very much for this wonderful talk, and we all enjoy your lectures very much. Here I have two questions. First one is the distinction between the dynamical equilibrium and say steady state non-equilibrium.
Steady state.
Yeah. Steady state non-equilibrium.
Steady state. So you're saying steady state non-equilibrium?
Non-equilibrium, where you have alternate dots subject to the voltage bias, where you have something, say, charge currents flowing from one side to another. So very much like the boxes that you mentioned, that you put something in, and in one box and another box that something is going out, So, but these two situations are different, right? So one is your case where the dynamical equilibrium. Another is indeed we have say a dissipative.
Sure. So
What is the
but I'm not sure I completely understand what you want to know. I mean, if so, we understand what it means to have a steady state. The steady state means time independent. Okay, if things are flowing, then they're not time independent, right? So if you have a pot of water and you're pouring water in and water is coming out at the same rate, the total amount of water in the pot is constant in time. So that's what I mean by a dynamical equilibrium, because the total amount of water in the pot doesn't change in time. But it is true that this is not a steady state, because water is going in through one hole and it's going out through another hole. And what that means is that water inside of the system is constantly flowing to equilibrate the system, right? Because, you know, if you have water coming in one side, let me draw a picture. Okay. So this is a system over here, okay?
Yes.
Now I'm going to drill a hole in one side and I'm going to drill a hole in the other side. And I'm going to have water going in. The water is going to go in this side and it's going to go out this side. So therefore, this is not steady because things are moving. I mean, the water that is coming in this side has to move slowly to get to the other side in order to go out. But if it can do that, okay, if the water can flow fast enough so that the total amount of water in this box does not get bigger or smaller, then I say the system is in dynamical equilibrium because the total amount of water in the box is constant in time. However, it is not a static system because water is going in. It's going. If something is going, it's not static, okay? And water is going out. So if it's going, it's not static. So it means that the system is in equilibrium, but the equilibrium is not static, it's dynamic equilibrium. It is exactly the same as if you have a top or a gyroscope. If you have a gyroscope, what does the gyroscope do? It is spinning and it is going around, it is nutating like this, and it is going around and around, right? But it doesn't fall down. So it is in a dynamic equilibrium because it does not fall down. If this gyroscope stops spinning, it falls down.
Yeah.
Okay. So you understand the distinction that I'm.
So here's my second question, which is related to the first one. So
Yeah.
Your very new so the counterintuitive results based on this complex span. Does it rely to the fact that we need to create a dynamical environment, such as the spinning top or something which flows this system so that to stabilize your the bound state in this dynamical equilibrium state, which means that if I don't inject, say, energy or something in your system, which means that there's nothing in, get injection system, nothing is getting out, and your results are not very easily to be observed. In other words, do we need to create the dynamical environments in a real experimental setup to observe this new phenomenon?
I think what you're asking is, I'm not sure, I couldn't hear all of the things that you said, but I think you're asking, what is the nature of a laboratory experiment in which we are looking at dynamical equilibrium? Is that your question?
Yeah, more or less, which are relevant for your theoretical results, right? So,
right. So,
how to realize this in the lab so that we have a dynamical equilibrium.
Right. So I can give you a simple mechanical example, if you like, where you have energy going in and energy going out. It's very simple. Okay, would you like such an example?
Yes, please.
Okay, well, suppose you have a rope. So this is just a rope.
Yes, I can see that.
Okay, and it is under tension. So this rope is being pulled pretty tight. So I'm pulling it this way and I'm pulling it this way. Okay, and now I have a pendulum hanging from this rope, and it is swinging back and forth. Okay?
Okay.
And I have another pendulum also swinging from this rope. So there's a rope, we have a pendulum, and this pendulum is swinging back and forth, and another pendulum is swinging back and forth. Okay?
Yes.
Now, these pendula, if this pendulum is swinging, it eventually will make this pendulum start swinging, because these pendula are coupled through this rope. They're not independent. So if I give this pendulum a push and it starts swinging, eventually the other pendulum will start swinging. Do you agree?
Yeah, I see your point. Thank you. This is exactly what I want to know. The real setup where you create dynamical.
Okay. Right. So what I'm going to do is I'm going to push this pendulum. Okay, so I will push it to make the pendulum swing, and I will put energy into the pendulum. Okay? But this pendulum, I will have this pendulum has friction. Okay?
Okay.
So energy is going into this pendulum because I'm giving it a push. But energy is going out of this pendulum because there's friction in this pendulum. Let's say it's swinging in water, or there's friction in the connection to the rope or something, okay? So I have two pendula, and I push this pendulum, but this pendulum has friction, okay? Now, that system, if there is a weak coupling between the pendula, what will happen? A very weak coupling. Well, because I'm pushing this pendulum, it swings higher and higher and higher, and it's getting bigger and bigger and bigger. It has more and more energy. Of course, it's losing some of the energy to this pendulum, but not very much. So the total energy in this pendulum is growing bigger and bigger and bigger, and the pendulum swings higher and higher and higher. Okay?
Yeah.
However, if the coupling of the pendula is pretty strong, then the energy from this pendulum can go into this pendulum. And so I put energy in this pendulum, I take it out of that pendulum,